Welcome back to the Piping Systems for Industrial Plants online course. You are watching the introductory video of Module 2, Fluid Mechanics. This video is a quick overview of the different contents you have to get acquainted with prior any development. The contents that will be covered in this module have been outlined to understand the design processes of piping transporting fluid, in order to arrive to an adequate design. Contents included in this module are flow of fluids in piping systems, properties of fluids, energy conservation principle, mass conservation principle, pressure loss, flow calculation, and diameter calculation. Fluid mechanics is the part of physics that deals with the action of fluids, static or in motion. Principles established by this branch will be applied to determine the diameter and pressure loss of a piping system. To achieve this, the following must be known: the properties of fluids, the fluid flow, laminar or turbulent, energy conservation principle, and the pressure loss equations. A fluid flowing through a pipe will always carry an amount of energy loss, which is spent in overcoming resistance opposing the flow and eventually dissipates in the shape of heat. The resistance that a pipe must overcome is of two types: external, resulting from the friction between the fluid against the pipe walls, acceleration and direction changes, and the resulting turbulence produced inside the pipe. Internal, resulting from the friction between the fluid molecules themselves against each other, in other words, the viscosity of the fluid. External resistance will be greater the higher the fluid velocity and pipe wall roughness, and the smaller the pipe diameter. On the other hand, internal resistance will be greater the higher the fluid velocity and fluid viscosity. The energy used to overcome these resistances is called head loss or pressure loss, in turn resulting in a gradual decrease in the pressure of the fluid, falling from one point to another in the direction of the fluid flow, pressure drop. Thus, the only fluid energy variation between the endpoints of the pipeline is the produced by pressure loss. Next, the Reynolds number and its importance will be explained. If small amounts of a colored fluid are injected in a water stream flowing through a glass pipe, and we observe the behavior of the colored filaments in the different areas after the injection points, the following will be seen. If the mean velocity of the stream is small, the colored filaments will be seen as straight lines, known as laminar flow. As the flow rate increases, these filaments continue to move in straight lines until a certain velocity is reached, where the filaments begin to curl, breaking in an abrupt and fuzzy way. This occurs at the so-called critical velocity. At higher velocities than the critical, the filaments disperse indeterminately throughout the stream, known as turbulent flow. The Reynolds number, dimensionless number, is a characterization of the flow in a pipe. Depends on the diameter of the pipe, the fluid density, fluid viscosity, and flow velocity. It may be considered as the ratio of the dynamic forces of the fluid mass with respect to the deformation stresses caused by viscosity. For technical studies, the flow rate in pipes is considered laminar if the Reynolds number is less than 2000, and it is considered turbulent if the Reynolds number exceeds 4000. Between these two values, the so-called critical area is found, where the flow is unpredictable, possibly being laminar, turbulent, or transition flow, depending on many conditions. The energy conservation law states that energy cannot be created or destroyed, can only be transformed from one form to another. For example, when electrical energy is transformed into heat energy in a heater. Bernoulli's principle states that along any flow stream, the total energy in two different sections of a system is constant, and it is formed by the piezometric heights due to pressure, the kinetic heights due to velocity, and the potential heights due to position, which is nothing different than the energy conservation law expressed in the terms just described. It is worth mentioning that each of these terms can be expressed in meters, linear unit of the MKS system. The flow of fluids in pipes is always accompanied by friction, produced between the particles themselves and between the fluid and the pipe wall. In other words, energy loss. It means that there is a pressure loss in the direction of the flow. If two manometers are connected to two different sections of a pipe with a running fluid, the manometer at the inlet section of the pipe will indicate a greater static pressure than the one located at the outlet section, due to the pressure loss. It is necessary to quantify this energy loss to be able to adequately design the piping system. Darcy's equation is the most universally used to determine the pressure loss in a pipeline, valid for both laminar and turbulent flow of any fluid in a pipe. The pressure loss depends on the friction factor, the pipe length, the velocity of the flow rate, and the pipe diameter. The most difficult part of Darcy's equation is to determine the friction factor, due to the fact that it depends on the Reynolds number and the pipe wall roughness. Finally, once the pressure loss in straight pipe runs has been determined, the pressure loss in fittings must be calculated depending on the system configuration. One of the most used methods to determine the pressure loss in fittings is the analytical method developed by Crane. Based on numerous laboratory trials and geometric likeliness of different fittings, this method establishes the friction factor for different sizes of new commercial piping, then a resistance coefficient for each fitting can be obtained. That, combined with Darcy's equation, yields the pressure loss of the fitting. The great advantage of this method lies within the programming possibilities, saving considerable amount of time. As explained before, the diameter of a pipe depends on the fluid flow required, the elevation of the inlet and outlet of the system, the pressure level at these points, the velocity and allowable pressure loss, the fluid nature, and piping material and pipe type. Except for the elevation of the inlet and outlet points of the system, all the other variables are related. The diameter depends on the flow. The flow depends on the velocity. The velocity depends on the diameter, and the pressure loss depends on the square of the velocity. Thus, to solve this system, it is necessary to iterate. In other words, The designer needs to adopt acceptable values of those variables representing a compromise between the pipe diameter and the pressure losses of the system. From all the values mentioned before, normally the parameter fixed is the velocity, since the diameter and pressure loss are a function of this. There are several publications and references that collect data from successful experiences, allowing designers to develop different projects. An example of this can be seen on the screen for steam, for example. There is not a unique solution when it comes to piping sizing. There are different solutions that bring different implications. Let's analyze the following. For a given diameter, a fixed velocity and pressure loss can be found. If the pressure loss of the system needs to be minimized, the velocity has to decrease, and therefore the diameter of the pipes will increase. If the capital investment of the installation needs to be reduced, the pipe diameter can be reduced, increasing the velocity of the system and thus the pressure loss. Summing up, reducing the diameter means less initial investment and more pressure loss, in other words, installed power. On the contrary, reducing the pressure loss will require slower velocities and in turn larger diameters. This video is just a quick overview of the different contents you have to get acquainted with. You should check and understand the different contents mentioned in this video in the study notes prior any development. Remember that all concepts dealt with are complementary and that assignments are linked. Keep up with the woodwork and come back for more. Thank you and have a great day.